Swayam Prabha. Digital India. Educated India.
Welcome. So, in the last lecture we have started looking at a constant factor approximation algorithm for metric TSP. We have seen a two factor approximation algorithm and we have also described a 1.5 factor approximation algorithm. So, in today's class we will prove and we will analyze and see a dry run of 1.5 factor approximation algorithm for metric TSP. So, 1.5 factor approximation algorithm for metric TSP. Okay, so let us see an example B A, B, C, D, E, F. Let us put some weights. Okay. So, now let us compute the minimum spanning tree and let us use Kruskal's algorithm. So, D is the shortest edge, shortest weight edge, and B F is also another shortest weight edge. These two we add, then A B, B C, and then A D, and then E F. This is one minimum spanning tree. Of course, there are other minimum spanning trees. So, what we do is that we first highlight the, or maybe let us take this, this will be more useful for showing the example algorithm. The other MS will also work, but this will elaborate the use of this algorithm more elaborately. What we do is that we first highlight the vertices which are of odd degree. So, C is of odd degree, E is of odd degree, F is of odd degree, and D. These are the 4 vertices. So, here is a graph theoretic result which is not difficult to prove, it is quite easy to prove, but let us not prove it, use it as a fact that in every graph the number of vertices of odd degree is even. Okay. So, here we have 4 vertices of odd degree. Next, what I do is that I look at the induced graph on these 4 vertices. So, here are the things D, E, C, f. Okay, and these are the edges. So, this weight is 1, this weight is 3, this weight is 3, between this there is a 4, and of course, the missing edges we assume they are edges of weight infinity. So, in this graph I compute, because there are it is a complete graph, and I have even number of vertices, there always exists a perfect matching. What I pick is a perfect matching of minimum weight. So, that will be a minimum weight perfect matching for this graph will be CE and DF. Okay. So, next what I do, I add these edges in this graph, in this tree. So, I add the edge DF and the edge CE. Now, what I have after adding the edges, you see that the degree of the vertices of odd degree has increased by 1, and hence after adding all the vertices will have even degree. Okay. And next what we will use next is what is called an Eulerian tool. Eulerian tool. What is it? Tour traversing every edge exactly once. Okay. This is an Eulerian tool, and here are a couple of facts. There exists an Eulerian tool in a graph if and only if the graph is connected and the degree of every vertex is an even integer, even number. Moreover, an Eulerian tool can be computed in polynomial time if it exists. That is, if the graph is connected and the degree of every vertex is an even number, then a Eulerian tool can be computed in polynomial time, and this is what we use next. In this graph, which is obtained by superimposing a matching on odd vertices with the spanning tree, it is a connected graph because it is it contains a spanning tree as a subgraph, and it is all the degree of every vertex is even. So, there exists a Eulerian tour, and let us compute the Eulerian tour, and it is easy. So, from A let us go to D, from D let us go to E, from E let us go to C, from C let us go to B, from B let us go to O, from O let us go to F, from F let us go to B, and then A, come back to A. Okay. So, what is the Eulerian tour here? A to D, E, C, B, D, F, B, and then A. Now, what we do here? We do a short circuiting. For example, from A I go to D because D is unvisited, from D I go to E because E is unvisited, from E I go to C because C is unvisited, from C I go to B because B is still unvisited, but from B I do not need to go to D because D is already visited. So, I directly go to F, okay, and then from F I do not need to go to B because B is already visited, I directly go to A, and because of triangle inequality, because of metric property, this short circuiting does not increase the cost of the tour. So, what is the tour here? Let us redraw the graph A, B, C, D, A, B, C, D, E, F, so, here are all the edges. Now, what is the tour? From A I go to D and then I go to E, A, D, E, C. So, from A I go to D, D to E, E to C, then C to B, B to F, C to B, B to F, and then return to A. Okay. So, this is the output. The output of the algorithm A, D, E, C, B, F, A. And so, and because of triangle inequality, so missing edges, so here is the preprocessing. For missing edges, edges are added with distance between its endpoints as weight. Okay, that is what we do. And also note that where are we using the metric property? Short circuiting. Because of metric property, or because of triangle inequality, short circuiting never increases the cost of the tour. Cost is sum of weights of the edges. Okay. Now, we claim that our algorithm is a 1.5 factor approximation algorithm. Okay. So, first observe that even without short circuiting, the cost of our edge is bounded above by this Eulerian tour. So, the alg is the cost of output tour. This is bounded above by cost of Eulerian tour. Since short circuiting never increases total cost due to triangle inequality. But what is the Eulerian tour consists of? It traverses all the edges exactly once, and there are two kinds of edges. One is spanning tree edges, another is this matching edges. So, this is weight of the minimum spanning tree plus weight of the matching on vertices of odd degree. Okay. Now, we have observed in our analysis of two factor approximation also that weight of an MST, weight of any minimum spanning tree is less than equal to opt. Why? Since a traveling salesperson tour TSP tour is a connected spanning subgraph of G input graph and an MST is a connected spanning subgraph of minimum weight. Okay. Next, what we claim is weight of the matching on the vertices of odd degree is at most twice opt. Half opt, at most half opt. Matching on vertices of odd degree is less than equal to opt by 2. Proof: let O be the set of vertices whose degree in the MST, in the computed MST is an odd number. And C be an optimal or an minimum cost traveling salesman tour. The first step is to short circuit the other vertices and have a shorter tour from C which is on O. So, short circuit the vertices not in O from the tour C to obtain a tour on O a tour, let us give it a name, tour say C prime on O. So, what is it? So, suppose here is C, this is a optimal travelling salesman tour. So, and where are the odd vertices? So, suppose these are the odd vertices. The vertices whose degree is odd and the other are even vertices, maybe these are even vertices, their degrees are even. So, what we are saying is that from C you short circuit C and visit only odd vertices. Okay, and this one we are calling it C prime. So, this is C prime. So, again because of triangle property, short circuiting any vertex, short circuiting any tour can only reduce its cost that is we have cost of O, cost of C prime is less than equal to cost of C, which is the opt. Okay. Now, you see that any circuit, this circuit C prime contains two matchings on this red vertices, on these vertices of odd degree. One matching is these white edges, and other is this these red edges. So, let us write, we observe that the tour C prime contains two matchings on O, and which edges we have added? we have added a mean cost matching on O. So, hence the weight of the weight of the mean cost matching, minimum weight matching of O is less than equal to the cost of C prime, because simply because C prime consists of two matchings on O and we have added this thing. So, this is this cost of C prime and it contains two matchings. So, this by 2, but this is at most opt by 2. So, hence we have the following alg is cost of MST plus cost of matching minimum weight matching on O. Cost of MST is less than equal to opt and cost of minimum weight matching on O is less than equal to opt by 2, which is 3 by 2 opt. Hence, alg by opt is less than equal to 3 by 2, which concludes the proof. Hence, we have a polynomial time three by 2 factor approximation algorithm for metric TSP. Okay. So, let us stop here today.